Greetings, ladies and gentlemen. In the previous lecture, we looked at what we call the minors and cofactors of a given matrix. And basically, we said that if we are interested in the minor of an entry AJ, then we basically look at the determinant of the matrix that will be obtained when we delete the ith row and the jth column of that given entry. And we can easily denote that with m of ij. We also talked about the cofactor of an entry, that after you have obtained the minor of that given entry, then you simply multiply by negative 1 to the power of I plus j. So when you get negative 1 to the power of I plus j, then you multiply by the minor of that same entry, then you will obtain the cofactor of that entry. We looked at some examples where basically we obtained what we call the minors and the cofactors of that given matrix. So today we want to look at the determinant of higher order matrices. The determinant of higher order matrices, and preferably we shall be talking about the determinant that has got the order which is greater or equal to 3. And the good news is that so far we already know how to obtain the determinant of a 3 by 3 matrix, and we already know how to obtain the determinant of a 2 by 2 matrix. So our interest will be to look at matrices that has got the higher order, for example, 4 by 4, a 5 by 5, like that. So basically, we shall be still using the idea of what we call the cofactors. And of course, to talk about the cofactors, you must talk about the minors. So it is very important that you know how best you can get the cofactor and how best you can get the minor of any entry within a given matrix. So let us talk about an n by n matrix. So if we need to obtain the determinant of a matrix A, which has got the order that is n by n matrix, so we shall simply consider the sum of the entries in any row or column multiplied by their respective cofactors. What do we mean? We are saying if you are having, for example, we'll take an example of a 3 by 3, A11, A12, A13, A21, A22, and A23. Then A31, A32, and A33. So when you want to obtain the determinant of this given matrix using the cofactors, then you will choose one row. You can choose the first row. You can choose, if you want, you can choose the second row, or you can choose the third row, any row that you need. Someone else can choose a column. You can choose the first column. You can choose the second or the third column. You will choose any row or a column of your own choice. Now, if I'm to choose, for example, the first column, then I will have A11 first. That is the first entry. Then to get the determinant of this matrix, let me call this matrix B. So to get the determinant of B, I will simply get this entry, which is here A11. I multiply by the corresponding cofactor, that is C of 1, 1, plus, then I add there, I'm considering the first row. So I can write it here, consider the first row. Consider the first row. So when I consider the first row, in the first row I have entries A11, A12, A13. So to get the determinant of this matrix, I will simply get A11 multiplied by the corresponding cofactor, which is C11. Then plus A12, the corresponding cofactor is C12, plus A13, the corresponding cofactor is C13. So what does this one mean? This one means that when you have these entries A11, A12, and A13, what you are interested in is to get the corresponding cofactor, that is C11, that is C12, that is C13. Then when you multiply this and get the sum, what you will obtain here will be your determinant. So this will be the determinant of that given matrix. So someone who will have considered this column here, for example, if you consider a column, then it means if, for example, you consider the third column, that is for someone else who chooses the third column. So it means you will talk about A13 times the corresponding cofactor C13. Then add there A23, then multiply by the corresponding cofactor 23. Then add there A33 multiplied by C33. So you have chosen this row. So get the sum, but as you get the sum, multiply each of the entries with the corresponding cofactors. So what you obtain will be the determinant, and it will be the same determinant as someone who has considered a row. So when you are given a matrix, choose one row, then consider that row, and make sure you also consider their corresponding cofactor. So this is what we are talking about. So you consider an n by n matrix, then the determinant of this matrix A will be the sum of their entries in any row or column multiplied by their respective cofactor. And that's why we are saying if you consider an n by n matrix, so when you consider an n by n matrix here, which n by n matrix can be written, let us try to write that n by n matrix here. Then we consider it, then after we shall be able to realize what we are talking about very well. So an n by n matrix, you can write it in this form. That is A11, that is A11, A12, up to A1n. We are considering an n by n matrix. So the next is A21, A22, up to A2n. The next one which goes up to AN1, AN2, up to ANN. So you are having your matrix there, A. So this is your general matrix. So if we want to get the determinant of this, so we have chosen the first, this one here, the first row. So to get the determinant of this, we are simply getting A11, but multiplied with the respective cofactor, that is C11, plus A12, this one here, because we have chosen this row here. So that is A12, C12, up to A1n, C1n. So doing that, we shall have got the determinant of this matrix here. So to get the determinant of a given matrix, choose a row or choose a column. Let us now look at some of the examples. Our example number 1 says we need to determine the determinant of this matrix. So this one here is 1, 2, 3, 4, 1, 2, 3, 4. This is a 4 by 4 matrix. And so we would like to determine its determinant. So we shall choose, like the way we have said, we shall choose one of the rows or one of the columns. But possibly I will choose one of the rows, and preferably I will like to choose a row number 3. The reason is when you look at row number 3, you realize you have some two entries which are zeros. which means this one here will not require much of the calculations, since you will only be considering two elements or two entries, 1 and 5. Because when you are to look at other rows, here you only have 1 0, here you don't have any 0 there. So which means if you are to consider this row, you will get the same answer. However, this one here might be more tedious compared to the third row, because you will consider this entry, you will consider this entry, consider this entry, consider that. All the 4 entries, you will need to consider them. And for the purpose now of time, you would now like to go with row number 3, because the only entries to consider within this are only 2, that is 1 and 5, in comparison to others. So let us consider the third row. We shall consider the third row and see how best we can obtain what we call the determinant. According to what we said, if this is our matrix A, for example, so the determinant of this A will simply be, if you are considering this row here, you will look at each of these entries, you multiply them by their corresponding cofactors, and at the same time, you should be adding them. So when I'm to consider this, so I would be in need of considering the first value, which is a 0, but multiplied with its corresponding cofactor. So this one here is in the third row, the first column. So it means it would be 3 1. So that is 0 times C, a cofactor 3 1, plus 1 times a cofactor 3 2, this one here. Then plus 5 times cofactor 3 3, plus 0 times cofactor 3 4. So looking at that, you can easily realize that this and this will cancel. This 1 times 3 C of 3 2 will remain C of 3 2. Then plus 5 times C of 3 3. So basically, to look at the determinant of A, we shall need the cofactor 3 2, we shall need the cofactor 3 3. So that is what we shall look at. We know how to get the cofactor 3 3. If you need the cofactor 3 3, it means you will have, if you need the cofactor 3 2, you will need to eliminate first, to eliminate 3, that is the third row and the second column. But remember, to do that, you need to be knowing the minor. So we need to first of all look at the interpretation of C 3 2. This one here is same as negative 1 to the power of 3 plus 2 times the minor of 3 2. Then if you need C of 3 3, is same as negative 1 to the power of 3 plus 3 times the minor of 3 3. So if we are to get C, the cofactor of 3 3 and the cofactor of 3 2, then we need to be knowing the minor 3 2 and the minor 3 3. But to get the minor 3 2, then you will eliminate the third row, second column. So when you eliminate the third row, second column, then you get the determinant of these remaining entries here. That is 6 2 negative 1, 0 negative 2 negative 1, 1 negative 4, and 1. You know how to get the determinant over 3 by 3. So let us look at that. So basically, I hope you know what C of 3 3 is representing, C of 3 2, but don't forget that we shall need to substitute them back here, since this is our determinant that we are interested in. So let us look at that. So we are saying that using the cofactor expansion along the third row, so that is what we are looking at. We are looking at the third row, and basically we are at this given point where we have C of 3, 2, and plus 5 of 3, 3. So this is our expression, which we can call maybe equation number 1. So from there, we need C of 3, 2, the cofactor of 3, 2. To get the cofactor of 3, 2, we have said it is same as negative 1 to power 3 plus 2, then times m of 3, 2. But remember, m is the minor 3, 2. Which minor 3, 2? We obtain by eliminating the third row, then second column. And basically, we talked about that. And this is the matrix that we shall remain with. Which matrix? We need its determinant. We need its determinant. This negative 1 is coming from negative 1 to power 5. Negative 1 to power 5 gives us negative 1. So we have to multiply by the determinant of the remaining entries after we have eliminated the third row and second column. And basically, you know how to obtain what we call the determinant of such a matrix. We shall maintain 6 here. Then, after maintaining 6 here, we shall try to eliminate. Let me try to do that. When we remove this one and this, we shall remain with the determinant of this. So that is negative 2 times 1 minus this one here, negative 2 times 1, which is negative 2. Then minus negative 1 times negative 1, of course it will be positive, so it will be minus 4. So that is what we shall get here. But remember, we shall maintain the 6. So we say 6 into the determinant of negative 2, negative 4, negative 1, and 1. So this determinant here is what we are having here. Then remember, we are supposed to subtract 0 into the determinant of, you will eliminate this and eliminate this. So it basically will remain with 2, negative 4, negative 1, and 1. But because we are multiplying by 0, it will remain as 0. Then we are supposed to add there. The last value is 1 times the determinant. When you eliminate this and the first row, you will remain with 2, negative 2, negative 1, negative 1. So getting this one here is a negative 2, which is this. Then we are supposed to subtract. So after subtracting, then you have negative 1 times negative 2, which is positive. So you have minus positive 2. So basically that is what we shall get. So when you try to simplify, should be able to get 40. So now next we need C of 3, 3, the cofactor 3, 3. And to get the cofactor 3, 3, we are saying cofactor is same as, by definition, negative 1 to power 3 plus 3 times the minor of 3, 3. But negative 1 to power 6, it remains positive 1. So that's why we are having 1 times m33, which remains m33. But what is the minor of 33? Minor of 33, we go back to the matrix, we eliminate the third row, third column. When we eliminate that, we should be able to remain with the determinant of this. That is 6, 4, 1, 2, negative 3, negative 4, negative 1, 0, and 1. We can easily see that from our matrix. When we look at the matrix here, this is our matrix. So we are trying to eliminate. In this matrix, we are trying to eliminate the third row, this one here. We are trying to eliminate the third row and the third column. When you eliminate this, you remain with 6, the determinant of 6, 4, 1, 2, negative 3, negative 4, then negative 1, 0, and 1. So this is the determinant that we are interested in. So when we get back, we can easily see that is what we are talking about here. 6, 4, 1, 6, 4, 1, 2, negative 3, negative 4, 2, negative 3, negative 4, then negative 1, 0, 1, negative 1, 0, 1. So this is the matrix we are talking about. That is the matrix that is obtained after eliminating the third row, third column. So from there, then look at the determinant, how to get the determinant of a 3 by 3. We are aware of that. So you maintain this 6, so you will have 6 times the determinant. So when you eliminate this and this, you will remain with negative 3, negative 4, 0, and 1. So you will get that. So minus 4, then again times the determinant, which you will eliminate this again, eliminate this. So meaning that you remain with 2, negative 4, and negative 1, and 1. Then again plus 1 times the determinant. After eliminating this and this, you will remain with 2, negative 3, negative 1, and 0. And possibly should be able to get this one here after you have thoroughly expanded the determinant. Of course, you will be able to get this, and it should be able to give you negative 13. So what do you realize from equation number 1? From equation number 1, where we said our determinant of A is basically C of 3, 2 plus 5 of 3 of C 3, 3, and you already have your C of C, your C, the cofactor of 3, 2, which cofactor of 3, 2 you got as 40. Then you will add there 5 times the cofactor of 3, 3, which cofactor of 3, 3 is negative 13. So you have negative 13. So when you try to simplify this, you should be able to get negative 25. So 5 times negative 13, it will give you negative 65. So 40 plus negative 65 should be able to get negative 25. So that would be our determinant. That would be the determinant of A. So from here, what you need to do is you need to choose any row, and from there, the row that you have chosen, then try to expand it by adding. So you get the sum of the entry multiplied by the corresponding cofactor. You know how to get the cofactor of any given entry. So from there, you will be able to get the sum. Someone might not necessarily have chosen the third row. A person can choose to use the second row, can choose to use the third row, can choose to use the fourth row, or you can use the columns. You can use the columns, but you should be able to get the same answer. So you will try it using the different rows and see if you are able to get the same answer. So next, you will try to look at this part 2 here. Choose any row, but most preferably you would choose this row here, because when you look at this other rows, then this row here would be very simple, because this and this are zeros already. So the only non-zero values are 1 and 1. So which means you can easily use this row here, and you will only need to basically consider the cofactor of this and the cofactor of that. But if you use like this fourth row, then you will need to calculate the cofactor of this 4, the cofactor of this value, the cofactor of this, the cofactor of that, which will be a bit hectic compared to a person who would have chosen the second row. So also, someone can also choose this column here, which is the first column. The first column is having 0, 1, 0, negative 1. It's also a bit simpler because you are having 0 here, 0 here. So which means the only cofactor you might need to calculate is the cofactor that corresponds to this, or the cofactor that corresponds to that. So which will be a bit easier in comparison to others. But all of them will give you the same answer, irrespective of the row or the column that you have considered. At the moment, I now believe that we are able to find the determinant of any given matrix. And for that case, we now need to come to what we call the inverse of a matrix, and basically by using its adjoint. Now, to determine or to get the inverse of a matrix, denoted by a to power negative 1, we shall be using this relation, that A inverse is same as getting 1 over determinant of that given matrix times the adjunct or the adjoint of the matrix A. And we are saying, to get this adjoint here, then we take the transpose of the cofactor matrix. Since we already know how to get the determinant of any given matrix, then the other important thing is to know how to get the adjoint of the matrix. But we know how to get the cofactor matrix. Since we know how to get the cofactor matrix, we shall be able to obtain the adjoint by simply taking the transpose of the cofactor matrix. So let us look at some few examples. The example number 1 says find the inverse of A, which A is given by 1, 0, 0, negative 1, negative 4, negative 1, 0, 5, 1, 5. So to use the relation for the inverse, that the inverse of A is 1 over determinant of A times the adjoint of A, then we need to get the determinant, we need to get the adjoint. But as we said, the adjoint is simply the transpose of the cofactor matrix. The transpose of the cofactor matrix. So we need to first of all look for the cofactor matrix. So here I've already summarized for you the cofactor matrix of C, which is this one. But let us see how best we can get the cofactor matrix. We already did this, so you should be able to confirm that your cofactor matrix is this, using the procedures that we looked at last time. But if we to recall some of the concepts about the cofactor matrix, we said that if we have our matrix, which matrix is A? This is the matrix we are talking about. So that is our matrix A, and we need to get its cofactor matrix. To get the cofactor matrix, first of all, you need to know the minors of each of the entries. Then after the minors, you can get now the corresponding cofactors. So that is what we have done here. So the whole process has been summarized below here. So to get the minor of the first entry, that is M11, we simply eliminate the first column, first row. So first row, first column is eliminated. Then you take the determinant of the remaining entries. So when you eliminate this one and this one, you possibly remain with negative 1, 1, 0, and 5. So you remain with the determinant of this. Which determinant of this is same as getting the product in the major diagonal minus the product in the minor diagonal. So that is what we have done here. 1 negative 1 times 5 is negative 5 minus 1 times 0 is 0. So we remain with negative 5. But we said to get the corresponding cofactor, you use the formula that negative 1 to power I plus j times the minor of ij. So that is what you use. But for our case, I is 1, j is 1. So we shall have negative 1 to the power of 1 plus 1, then times the minor 1, 1, which is negative 5. So negative 1 to power 2, negative 1 to power 2 times negative 5 will of course give you negative 5. So that is the negative 5 we are having here. So the same applies for all the entries. So to get the minor 1, 2, to get the minor 1, 2, you will eliminate the first row, second column. When we do that, we shall remain with negative 4, 0, 5, 5. We shall remain with that. So negative 4, 0, 5, 5. Get its determinant, and its determinant will of course give you negative 20. Then after that, get the cofactor, which is negative 1 to the power of 1 plus 2, and times negative 20. Of course, this one will result into a negative 1 times negative 20. It will be positive 20. So do the same for minor 1, 3. Eliminate the first row, third column. When you eliminate the first row, third column, you will remain with negative 4, negative 1, 5, and 1. So get its determinant. This will be negative 4. This will be minus negative 5, which will possibly give you 1. Then get the corresponding cofactor, which will give you 1. So do the same for M21 to get C21, M22 get C22, M23 gets C23. Do the same up to when you reach at M33. being the same, we shall be able to obtain MC3, and MC3 obtained should be able to give you -1, that is -1, and the cofactor of 3 should also give you -1. So having obtained the minors and the cofactors, we are interested in getting the cofactor matrix, and the cofactor matrix will be containing the cofactors of each entries. That one is, we begin with -5, -5, then we shall have 20, we shall have this one here, we shall have 0. So we are having -5, 21, -5, -5, 20, and 1. Then next we shall have, that is for 2, that is C21, C21 we shall have 0, we shall have 5, that is C22, then we shall have -1. So 0, 5, -1, 0, 5, -1, 0, 5, -1, that is in the second row. Then the third row we shall have, in the third row we shall have C31, 0, then 0, then we shall have -1. So that is 0, 0, -1. So this is the matrix containing the cofactors of each of the entries of our matrix A. So from there, since we are interested in getting the adjoint, and remember that the adjoint is same as the transpose of the cofactor matrix. So we shall need to get the transpose of the cofactor matrix. So remember that to get the transpose of this matrix here, what has been the row will become the column. So this was -5, 21, so it will become the column -5, 21. This is 0, 5, -1, 0, 5, -1 in the column form. This one is in row form, so it will become in the column form. So clearly, we are able to get our C, which is the cofactor matrix, as -5, 21, 0, 5, -1, 0, 0, -1. So we should be able to relate it with this one here. So clearly, we can easily relate it with this. This is our cofactor matrix. You should be able to do it very well and get this cofactor matrix. So from there, we have obtained its adjoint, which adjoint is same as the transpose. And if you try to relate it with the transpose we have obtained here, -5, 0, 0, 20, 5, 0, 1, -1, -1, you should be able to see that it is the same here. It is the same. So we have taken the transpose of this matrix. We have taken the transpose of this matrix to get this. So from there, what else are we remaining with? We are remaining with getting the determinant now. Since we have got the adjoint, then the next is to get what we call the determinant. So how do we get the determinant? If you recall from what we have talked about, to get the determinant of a matrix, I will choose a row within that given matrix. So let me choose this row, because we are choosing this row with the advantage that this row here is containing most of the entries zeros. So when it is containing most of the entries zeros, it will be the easier row to consider. So you can easily consider this row, or you consider this column here, 0, 0, 5. Still you will be able to get the same answer. So to get the determinant of this matrix A, let us consider the first row. If you consider the first row, so the first entry is 1. So we are supposed to have like A11 times the corresponding cofactor C11 plus A12 times the corresponding cofactor C12 plus A13 times the corresponding cofactor C13. Consider one row, or you consider one column. Then from there, since we have already got the cofactors, then it will be easier for us. So A11 is 1, C11, the cofactor C11 is -5. So we shall have -5 plus, this is 0, C12 is 20, so this is 20 plus A13, which is 1. No, A13 is 0, so we have 0 times C13, which is 1. So from there, we can easily see that the determinant of matrix A will be negative 5, which is same as this value here. So from there, that is for the person who considered the first row. But what if the person considers this third column here? We said the two must give you the same thing, whether you choose the row or you choose the column of your own choice. When you choose, for example, this is okay, this is done. But let us look at for the case of a person who has chosen this column here, whether we shall be able to get the same answer. When you choose this column, that is column number 3. When you choose column number 3, then the determinant of A will simply be, this entry here is A13 times the corresponding cofactor 13, plus this entry here is A23 times corresponding cofactor 23, plus this entry here is A33 times C33. So like that. So from there, you are able to get A13 is 0. Of course, it will be 0 times the corresponding cofactor 1. Then plus this one is 0 again times the corresponding cofactor -1. The next is A33, which is 5 times the corresponding cofactor -1. So clearly this will be 0, this will be 0. 5 times -1 will also be -5. So you realize you will all get the same answer there. So we have seen that our determinant is -5. So you choose any method that will be easier for you to get the determinant. So having got the determinant of A, then we shall now get what we call the inverse of A, because we have the determinant and we have the adjoint. So let us use the relation to get the inverse of A. So what will be the relation? The relation is that A inverse is same as 1 over determinant of A, then times the adjoint of A. So the adjoint of A is same as the transpose of the cofactor matrix. So clearly, we shall have 1 over determinant of A is -5, as we have seen. Then we are multiplying by the adjoint, which is same as the transpose of the cofactor matrix. -5, 0, 0, 20, 5, 0, 1, -1, and -1. So this is our adjoint. So multiply the two, multiply 1 over -5 to each of these entries, and we should be able to get this matrix here. So -1 over 5 times -1, we should be able to get 1. Multiplied here should be 0, multiplied here should be 0. -1 over 5 multiplied in 20 should be able to give you -4. This one multiplied on 5 should be able to give you -1. Then 0, 1, -1 over 5 multiplied in 1, you should be able to get that. Should be able to come up with that inverse. So basically those are the few procedures we follow to get A inverse. So what is most important here is that when you are getting the inverse of a matrix using its adjoint, especially when it is 3 by 3 and above, that is 4 by 4, 5 by 5, then you need to think about using the cofactor matrix. And after getting the cofactor matrix, take the transpose to get what we call the adjoint. After getting the adjoint, then multiply it together with 1 over the determinant of that same matrix, and you will be able to get the inverse of the matrix. So from there, I hope you'll be able to try some few other questions there and see whether you are able to get their corresponding inverses. So these are some of the few questions that you will try. So we need to find the inverse of the following matrices using the adjoints. So try to look at each of these, that is A, B, and C. First get the cofactor matrix, first get the cofactor matrix of A. After getting the cofactor matrix, take its transpose. After taking the transpose, again get the determinant, and after getting the determinant, use the relation 1 over determinant of that matrix times the adjoint, which adjoint will be same as the transpose of the cofactor matrix. So you should be able to get the inverse of A, to get the inverse of this B, and to get the inverse of this A. At the moment, I assume that everyone now is able to find the inverse of any invertible matrix. If that is the case, we shall then look at how best we can use the inverse of a matrix to solve a system of equations. So we shall be considering a square system of equations. In other words, we are to consider the equations in which we have the same number of equations as the variables. Now let us consider this theorem. So we are saying the theorem is for the theorem of equations with unique solutions. And we shall say if A is an invertible matrix, then the system of linear equations, which is in the form of AX equaling to B, will have this unique solution, and that solution will be given as A inverse times B. We can prove that. We are saying that if we have a system which can be placed in the form of AX equaling to B, this A is simply a matrix of the coefficients. It's simply the matrix of the coefficients of the variables. Then this X is the matrix of the variables, and this B is the matrix of the constant terms. We shall understand better when we come to some of the examples. Now, let us first of all show that if A is invertible, then the solution to this system here will be given by X equaling to A inverse times B. So since A is invertible, we can say that A inverse or its inverse exists. And if its inverse exists, then we can say that let us multiply this inverse on both sides of this given expression. That is AX equaling to B. So we are multiplying A inverse on both sides. So let us begin with A inverse times B. So in other words, we shall have A inverse times AX equaling to A inverse times B. And if that is the case, since this is multiplication, we can easily say, let us get A inverse, multiply it with A, then after we shall multiply it with this X. So from there, this is equal to A inverse times B. But we understand that A inverse times A is actually an identity matrix I. Then times X, which is equal to A inverse times B. But an identity matrix times any given matrix, you remain with the same matrix, meaning that X is same as A inverse times B. So we can clearly see that if A is invertible matrix and we have a system of linear equations in the form of AX equaling to B, then the solution will be given by A inverse times B. So let us look at some few examples. Our example number 1. We need to use an inverse matrix to solve this system here. That is 2x plus 3y plus z is equal to -1, 3x plus 3y plus z is equal to 1, 2x plus 4y plus z is equal to -2. So first of all, we shall need to express these equations here in matrix form, since we need to use the inverse matrix. So let us place these equations in matrix form. So in matrix form, we shall have the first equation, take the coefficients 2, 3, 1, 2, 3, 1, then take the coefficients for this, that is 3, 3, 1, take the coefficients for this, that is 2, 4, and 1. So that is the matrix containing the coefficients of x, y, and z. So here we shall have x, y, and z, and this one is equal to the constant terms. We have -1, we have +1, and we have -2. So in matrix form, we can have this system here written as this. So clearly we can easily see that this is in the form of ax equaling to b. It is in the form of ax equaling to b. So if that is the case, then remember that the solution to this system will be given by x, which is equal to A inverse times B. So what are we interested in? We shall be interested in getting the inverse of this matrix here. That is matrix A. So this one here is representing A. This X is representing the variables X, Y, Z. This B is representing this matrix, -1, 1, and -2. So in other words, we are saying A is representing 2, 3, 1, 3, 3, 1, 2, 4, 1. This is your A. X is representing X, Y, and Z. X, Y, and Z. Then B is representing -1, 1, and -2. And we are saying the solution is given by this. The x, y, z will be equal to A inverse times B. Now, we are interested in getting A inverse first. We have already looked at how best we can get the A inverse. So, using the previous methods, please look at the inverse or get the inverse of this matrix 2, 3, 1, 3, 3, 1, 2, 4, 1. So get the inverse of this matrix, multiply it with this B, and that will be your answer. You should be able to confirm the inverse that A inverse will be given by. So I will simply give you the A inverse, but make sure you confirm that A inverse is the same, looking at all the procedures or all the methods we have seen for finding the inverse of a given matrix. So we can easily see that A inverse is same as this. So this is our A, which we have already talked about. And next, if we have got our A as this, next is to get its inverse. So confirm that the inverse of this matrix is this by using the different methods we have seen in the previous sections. So if you are able to confirm that your inverse is this, then we are interested in getting x. So our x will be A inverse of B. Our x will be A inverse of B. Let us use the capital X to differentiate between the small x, since we already have in our expression the small x. So not confuse the two. So our x will be same as A inverse times B. Clearly, we have seen our A inverse as negative 1, 1, 0, negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, and negative 3. So you are having x equaling to A inverse times B. So your B, we have seen our B is negative 1, 1, and negative 2. So we can easily see that from the system here. So we have our system, which B is this value here, negative 1, 1, and negative 2. So that is the one we are talking about as our B. Negative 1, 1, and negative 2. Then this is our A inverse. So now, having that, we need now to multiply the two and remain with the value of x. So multiplying the two, we are having A inverse multiplied in B. So you will multiply normally, multiplying row by column. Multiplying row by column. So you will multiply this row into this column. So if we can try to multiply that, you will have negative 1 times negative 1 plus this 1 times 1, 1 times 1 plus 0 times negative 2. Then next you will have this row into this column. That is still negative 1 times negative 1 plus 0 times 1 plus 1 times negative 2. Still you will have the third row into this column here, which is 6 times negative 1 plus negative 2 times 1 plus negative 3 times negative 2. So that is what we shall have. But when we try to simplify this one is 1, this one is 1, this one is 1, but this is giving us 0, so 1 plus 1, it will give us this 2. This one here is 1, this is 0, this is negative 2, so you have 1 plus 0 plus negative 2, which is negative 1. Next you have negative 6 minus this one here is minus 2. Then this one here is plus 6. So when you look at this, you will remain with negative 2, which is the value that we are having here. So in general, you have seen that your x is same as 2, negative 1, and negative 2. So if this is your x, but remember x is representing the matrix, which is x, y, and z. So you will have x, y, and z equaling to 2, negative 1, and negative 2. So when you have such matrices here, then you will be equating the two matrices. And if you are equating the two matrices, for these two matrices to be equal, then the corresponding entries must be equal. So for that case, we shall say x is same as 2, y is same as negative 1, y is equal to this, z is equal to negative 2. So you will have got the values of x, y, and z. Let us now look at part B, which part B says we need to use the inverse matrix to solve for the values of x, y, and z when we have these equations, this one here, this one here, and this one here. So we have 2x plus 3y plus z equaling to 4. We have 3x plus 3y plus z equaling to 8. 2x plus 4y plus z equaling to 5. So we need to come up with the values of x, y, and z by using what we call the inverse of a matrix. So, like the way we have done in part A, we shall use the same technique to deal with part B. So first of all, we need to place these equations here in matrix form, and in matrix form we shall have it as 2, 3, 1. We are taking the coefficients for this equation. The coefficients for this equation 3, 3, 1. The coefficients for this equation 2, 4, and 1. So next we shall multiply by the variables x, y, and z, and this must give us the constant terms. We have 4, we have 8, and we have 5. So looking at this, it is of the form AX equaling to B, where A will be represented by this matrix here, where X represents this matrix here, and this B is representing this matrix here. But when we look at this matrix here, it will be the same matrix as the one that we had in part A. Because when you look at part A, you have 2, 3, 1, you have 3, 3, 1, you have 2, 4, and 1. So this matrix A will be the same, and for that case, it means the inverse, A inverse, will as well be the same. So since we have already got the inverse of A in part A, then we shall use the same inverse in part B. But what only changes is the matrix B here. So this matrix is the one that changes as in comparison to part A. So meaning that we need the values of X, Y, and Z by using the relation that X is same as A inverse times B. So since we already know the A inverse from part A, then we shall multiply by B, and we get the value of X, which X represents X, Y, and Z. So let us try that one out. So looking at part B, so looking at part B, we are saying X is same as A inverse times B. This is our inverse. We said the inverse for A is same, the inverse in part A is same as the inverse that we shall use in part B, because we are considering the same A. So that's why we are having this inverse here, and this inverse we shall multiply it by B. Our B is 4, 8, and 5. 4, 8, and 5. Then use matrix multiplication and see if you are able to get this matrix for 1 and -7. So multiply row by column and get this matrix for 1 and 7. So from there, it means your X will now be, after multiplying A inverse with B, 4, 1, and 7. But remember, this X is representing X, Y, and Z. So since this X is representing this, and this matrix to be equal to this one here, then X must be 4, Y must be 1, and Z must be -7. So we have -7 here. So that is basically what we shall get as the values for X, Y, and Z by using the inverse of A. So if that one is very okay, I hope you will be able to again try this number here, that is for part C. Part C, you look at part C, you realize in part C, actually also the A will be the same. A will also be the same in part C, because you realize that you have 2, 3Z, 2x, 3y plus z. So you realize that the matrix A will be the same, since all these ones are the same. So what will be changing will be matrix B. So to get X, Y, and Z, simply multiply A inverse. You will use the same inverse as we have used it in part A and B. Then you will multiply by the B, which B for this case will be the matrix 0, 0, 0. So get your A inverse, multiply by 0, 0, 0. That is the matrix B, and be in position to obtain the value of X, Y, and Z. So that is what exactly will be done for the part C. So using the same idea, you should be able to look at these other numbers here. So try these questions here and see if you will be in position to get the values of X, Y here, to get the values of X1, X2, and X3 in this system, and to get the values of X1, X2, X3 also when you are considering this system here. So try out these a few numbers here, and that is possibly where we shall start from next time. Thank you for watching. I wish you all the best. God bless you.